Hello, good morning to everyone. Here we have Professor Sushmita and Professor Etienne with us. This is the first in a series of plenaries that we are opening to a wider public. So expect in the future having more sessions like this. Today we have the honor to host these two distinguished speakers. The first one will be Professor Etienne Riviere from UCLouvain. I don't know if I mentioned it properly. He will present in the first half an hour, and he will be speaking about demystify the upcoming dark shading evolution of Ethereum and its associated data availability layer. After that, we will have Professor Sushmita from Faculty of Engineering, lead at UNSW Institute of Cybersecurity. Will guide us through the topic of post-quantum cryptography for blockchains, okay? So please, Etienne, the floor is yours, and yeah, good luck and enjoy.
All right, thanks for the introduction, and thanks for having me here. I'm glad to be here and talk about some of the recent work we've done and this upcoming Danksharding evolution of Ethereum. It's something that is still being discussed by the community and with lots of different designs that are discussed, and I hope that we'll shed some light on where all of that is going and what it's all about. So let me start by making a small introduction about something you might all know, that Ethereum has a severe bottleneck in its throughput. Okay, you have more decentralized apps that are being deployed, you have more transactions between accounts, and all of that consumes space in the blocks that are in the main chain, which we also call layer 1. And these blocks have limited capacity, and that means that you can't put more than a certain number of transactions. So you have the math here, and essentially we have one block every 12 seconds, and those blocks contain like a few 100 kilobytes at most of transactions. So effectively, the number of transactions you can have per second, and that depends obviously on the complexity of those transactions, is less than 20. So that's very limited. So that's okay for some decentralized finance applications. But if you want to have applications that have a higher volume of transactions, that can become a problem. So the main question is, how can we support a massive increase in this number of transactions per second, and therefore a massive increase in the number of the apps? So if you look at the Ethereum Foundation roadmap, where they eventually want to go, they said that they want to support 100,000 transactions per second. So we are clearly very far from that when we look at the current number. So what are the options we have to scale out Ethereum? So a pretty obvious one would be to say, well, let's just use larger blocks, or let's generate blocks more frequently, right? So that's obviously the easiest way, but that's a problem when it comes to maintaining decentralization. So decentralization is the ability of ordinary nodes to participate in the system, and not only beefy nodes that are operated by a few players. If you increase the size of blocks, then you have to verify these blocks, you have to broadcast them to all the system, and all of that takes resources, and you essentially put aside the smaller players. So that's a problem. So there have been discussions on how we could do to scale out Ethereum, and the first idea was to use data sharding, the idea of having different chains, and those different chains maintain a subset of the state of the entire chain, and then you have transactions that access state in one of these chains. But the problem is that if you access state in different subsets of the chains, then you have very costly cross-shard transactions. And it essentially was dismissed in the end, or it faded out of fashion because of all these problems about the fact that Ethereum has these very complex patterns of transactions that access state in multiple accounts, okay, or smart contracts. And that essentially leads to most of these transactions to be cross-shard and essentially complexifying the system and not yielding the scalability we were hoping for. So from 2020 on, the shift, the new focus has been on a rollup-centric roadmap. Okay, and the very idea, I'm going to go into the details in the next slides, is to have still the layer one with those ordinary blocks and a single chain that provides strong consensus and very strong decentralization, and also data availability, while a different subsets of layer twos, which are these independent systems that are attached to layer one, provide execution scalability. So what do we mean by layer twos? And I'm going to focus mostly on rollups, which are the most successful or type of them. Essentially is to build an independent chain that lives its life on the side, but its state is periodically anchored to the L1 chain. How do we do that? We have a state that is essentially the set of accounts that you are maintaining in that independent chain, and you take the state and you register a snapshot. So that could be, for instance, you build a Merkle tree. It's a data structure that contains all these accounts, and then you have a hash of multiple hashes that you can store on the chain, and anyone can check that the state of the chain corresponds to this anchored state in the L1. A rollup is essentially similar to your typical blockchain. You have a mempool that stores transactions that are pending execution, and you have nodes that essentially groups those transactions into blocks and then registers the results of these blocks, essentially the state changes, to the L1. So it's quite interesting to see that in all these rollups, and essentially all L2s, your transactions are not executed by the L1 nodes. You have L1 nodes that are your typical Ethereum validators. They do not check or execute any of the transactions that are executed by the L2. They only have the smart contract that can store this hash of the state, but that's it. The rollup participants, in contrast, they actually have to verify them. And there are two essentially families, two main families for that. You have optimistic rollups where transactions are considered valid by default, and they are shared with all the rollup participants, and participants can check that everything is fishy, and then if that's the case and if they are right, they can get a financial reward by submitting a fraud proof. Okay, and they have typically a few days for doing that. You also have more complex zero-knowledge rollups that essentially use zero-knowledge proofs to verify that the set of changes corresponds to the execution of the actual transactions. Right, so the main topic of this talk will be about sharing the transaction data. So the rollups, they commit state roots to the L1 chain using a specific smart contract, but you still have to share and disseminate the set of transactions, typically in the compressed format. But this means that you need to have a data availability layer. You need to have a way for all the rollup participants to share this data amongst themselves in order either to verify the transactions and submit fraud proof for optimistic rollups, or to verify the zero-knowledge proofs for zero-knowledge rollups. And there are essentially two options here. A rollup designer, they can say, well, we are going to build our own peer-to-peer or cloud storage for disseminating these transactions, and we're going to operate our own network. Okay, there are some systems like AnyTrust or Validium that have done that, but it essentially means that you have multiple P2P network that will coexist with the one that Ethereum already operates. So that's complex to operate. It's hard to properly secure. You have small networks that are more prone to DOS attacks and so on. And if someone wants to build a new rollup, then if he or she has to build an entire new P2P network, that's going to be a problem. So in order to massify the use of rollups, it's better to actually support this data availability as a layer one service, something that Ethereum provides and not something that rollups have to build by themselves. And in this talk, for the rest of this talk, I'm going to focus on that second option. So in the past, the only way you could actually share this L2 data, this set of transactions through the L1, was to actually make it part of the block space. So that was very costly because you have to essentially use real transactions that will stay in the chain forever and that have this binary data. You can call that cold data transactions, and that obviously competes with other L1 transactions, and that's extremely costly as a result. So for that, the community introduced a new mechanism, which is called EIP 4844, sometimes called also proto-Danksharding, both because it's a prototype of Danksharding and because also it combines the names of the two proposers. And the idea here is to make this L2 data not part of the main blocks, but as part of side data that is accompanying the block. Okay, and you have essentially in the block some small transactions, which we call block carrying transactions, that are attached to some blobs that are binary data objects that L2s can use. But you only have a limited amount of them, 3 to 6 blobs of up to 128 Ks. So is that enough? Well, not quite so, because if you look at how much data you can share that way, it's less than 1 megabyte per block. Okay, if you want to have rollups that help Ethereum scale to 100,000 transactions per second, that's clearly not there. It's better, but it's clearly not there. And again here, we could say, well, why don't we allow to have many more blobs attached to every block? And in that case, we would scale out very easily. Well, the problem here is that this blob data that is attached to the blocks, it has to propagate to all the nodes in Ethereum. And we are facing the same problem I've mentioned earlier when discussing the possibility of increasing the block size. The more blobs you have, the more data you have to broadcast in the system. And even if that data is not checked by the validator nodes in Ethereum, in the end, it has to spread, and if it might prevent decentralization. So you have an intrinsic limit here in how much data you can attach. Maybe a few megabytes could be okay, but more than that, you're going to face a problem. So the idea we can have is, can we simply do better by not spreading that data to all the nodes in the system, but instead sending small amounts to each node, okay, such that the entire network, the network as a whole, has all the data, but each node only has a subset of that data, right? So you have all these Ethereum nodes that consist of that form the infrastructure. They will only receive a subset of that data shared by the L2s. And then the L2 nodes, they may, identify which node of the L1 has the data they need, and then they can query those specific ones. Right? So that's a pretty straightforward idea, but putting it into practice is a little complex. And now we do that. We do that with this idea of DAS, or for data availability sampling, right? So the idea of data availability sampling that was introduced not in the Ethereum community, but in other systems before, is not to attach all the blob data that is the transactions shared by L2 in full to all the blocks, but to send that in subsets to each the nodes in the system, right? And the key idea here is that the validator nodes, they do not check that the L2 data, all the transactions are there by simply downloading them, but they only check that they are available in the system. And here, because we are in the decentralized systems where we may have some malicious nodes, we have to face problems where the proposer of the block that is supposed to attach all these blob data with the block could be malicious, could try to attack a specific rollup or the data of a specific rollup for whatever reason, or he simply might be lazy and doesn't want to propagate that data, or simply didn't put it together in the first place. So this is what we call the data withholding attack. It's like you make some data unavailable, and then the block might be accepted, but it has block carrying transactions that do not correspond to data that was actually shared. Okay, and if we share data in plain, a single bit missing means that the entire blob data is unavailable. And if some blob data is unavailable, the rollup might fail because it can't check the transactions, and you have some very annoying consistency problems. So what's the key idea to solve this problem is to have some form of redundancy. And the redundancy here will be in the form of erasure codes. Erasure codes allow you to take some pieces of data and add code so that when you have a subset of these pieces of data, you're able to reform or to reconstruct the entire data. So now you can lose some data. As long as you can reconstruct it, you're fine. Okay, and how will the nodes check that this data is there or can be reconstructed? They will do that using sampling. They will check for the existence of some data in the network and get high probability guarantees that the data is there. Okay, and this Danksharding idea, which is still as a roadmap for Ethereum, is this implementation of that very principle. And I will go into some details with this figure here. The idea is, as you see on the top left side here, you have a block with the regular transactions, and it is attached to up to 32 megabytes of L2 data. Okay, so this is what is represented in blue as this Sol matrix here, 256 times 256. It's organized as a two-dimensional matrix, and essentially this two-dimensional matrix will be extended using erasure codes to form what you have on the right here. Okay, so now each line and each column of that matrix will be extended to twice its size. So now we are switching from 256 to 512, such that if you recover half of the cells from a certain column or half of the cells from a certain row, then you are able to reconstruct that column or that row. Okay, I'm going to spare you the details of the rows. Just know that they have still these blob carrying transactions that are in the main block, in the regular Ethereum block, that allow to match that the data is what it should be in each of the cells. Right, so now we have this big blob of 512 times 512, and this is what will be shared in the network. So why do we use two-dimensional coding? We could say, well, we know how to do codes with one dimension. I could say I have my 32 megabytes of data, and I could add, for instance, 16 megabytes of codes. And then I know that any 32 megabytes of the result would be enough to reconstruct. Actually, the idea of using two-dimensional coding is very smart here, because you can do the codes on the level of these rows and columns. So it means that if you need a particular cell, you are L2 and you need a particular cell, but that cell is actually not in the network, or you could not locate it, you only have to recover a corresponding row or the corresponding column, right? The other thing that this brings you is that it makes it extremely hard for the proposer of the block, the entity that sends the block out in the system, to make a specific cell unavailable. Okay, if an attacker wants to make a specific cell unavailable, then it has to prevent a little more than a quarter of the data in this 512 type 512 matrix from being available in the system. So that's very unlikely that it will go unnoticed. Okay, and how will we actually notice that the data is indeed not available? We will do that by sampling. So that means that the nodes in the Ethereum network, they will check that the data is available by sampling for its presence in the network. They will choose a number of cells randomly, okay, and they will go and fetch those cells. And if they successfully check those cells, then they can have a certain probability or a certain guarantee that the data is available as a whole. Okay, so if you use 73 cells, okay, so this is, I'm sparing you the math here, but you have a false positive probability that is below 1 over a billion, right? And you can make that higher if you wish, but that's already pretty good. So what's the impact that is expected from that? Well, first, increased scalability. That's what was introduced in the first place. You now have 32 megabytes of blob data that comes with each L1 block. So that means that all the rollups can actually attach substantial data to support their operations. And also because there is more data available, then the fees associated with this data is much lower than what it is currently. Okay, so now we have an economy for the EIP 4844, where there is a fee market for blob space that is attached to blocks. And it's obviously cheaper than the regular block space, but still not that cheap, not cheap enough. Having more space means that we hope that the cost will be less. The idea is also to limit state bloat. So you know that an Ethereum node has to keep all the blocks since the very beginning of the chain. And obviously that costs some disk space. Here, the L2 data under this DAS principle is only stored for the time it takes for the rollups to verify it. Okay, so that's typically 18 days, and then it can be discarded. Okay, so the very idea of this rollup-centric design for scaling Ethereum is to really have execution on L2s, and then the L2s have their transaction data that they attach to the L1 that now specializes in settlement and makes data available through this Danksharding mechanism. Right, so now that we've covered how this idea works, because it's still an idea, and the main question that we have is how do we implement it? Okay, and that's not an easy one, because you now have a system where you have these 32 megabytes block that has been extended through Azure codes, and then you also have some metadata and some proofs that attach to it. So in the end, we have 144 megabytes of data that must spread to the network. Okay, ideally with some redundancy, because nodes may fail, some nodes might be lazy, or some might be unavailable. So we want to have some redundancy on top of the actual erasure codes redundancy. And we want that data to be easily fetched and located by the holder of blob data, essentially rollup participants. Okay, so that means that we have a networking problem, okay, and we are operating at the scale of Ethereum, so that means we are on a wide area network with nodes spread all over the world, and that has to happen quite quickly, okay? So why does it have to happen quite quickly? Because to make sure that a block is valid, we need to make sure that the blob data that is attached to that block through these blob carrying transactions is also valid. It means that it is also available in the system. Okay, and for to understand what it means, we have to go a little bit into how the Ethereum consensus works. Okay, so in a single slide, the Ethereum consensus works essentially in 3 phases. Okay, so we have a slot, what we call the slots. It's every 12 seconds, there is a new block that is generated. Okay, so a node that is called a proposed a block. We will see that this block is actually generated by a builder, but that's not important for now. And this block is propagated to all the nodes. Okay, and some of these nodes are part of a consensus committee. So that's something that is decided as part of the proof of stake mechanism of Ethereum. A committee is decided, and this committee essentially checks the blocks and produces attestations. Those attestations are shared in the second phase to all the nodes, and some of the nodes aggregate them, and then nodes can decide in the third part, okay, from 8 to 12 seconds, whether they consider the block to be valid or not. Okay, so this is how it works for regular blocks in Ethereum, and a block is a few hundred kilobytes at most, so it works pretty well. You can broadcast the block to all the system and get all these attestations within the first 4 seconds, and then in the next 4 seconds, you can get the aggregates of the attestations, and then you can finalize. But now, if you also have to make sure that the blob data that is attached to the blocks is available, it becomes a little tricky. Okay, with EIP 4844, you only have a few kilobytes of blob data that is attached. You can easily spread it out in the first 4 seconds. But now you have a more complex operation where you have to send data that is erasure coded to all the nodes, and then they have to sample for its existence in the network. Okay, so that means that now the community has been debating on how we should do that. Okay, and there are essentially 2 options. Okay, a first option is to say we don't want to change the Ethereum consensus model. We want to keep that after 4 seconds, the nodes that are part of the validator committee, they decide that the block is valid and that the data is available as well. So this is this tight fortress rule. You sample and you verify the blob data before voting or producing an attestation. Okay, so that seems like the right way to go, but the problem is that you have to do all of that within 4 seconds, okay, because the attestations have to be produced by these 4 seconds. And the other choice is to say, well, it's not possible. We're just not going to make it. Let's postpone. Okay, let's postpone and let's put this check of blob data availability to later. And that's called the trailing for choice rule. We have a lazy sampling that is after block issuance. So what does it mean? It means that if you have a block that is considered valid, but then we realize that the data that was associated with it is not available, then this block might be eventually invalidated. Okay, so the trailing fork choice is obviously easier to implement because you have less requirements, but you have new attack vectors. And for the interest of time, I'm not going to go into the details here, but in very short, this essentially introduces a time window where an attacker can exploit the uncertainty in the system. Okay, you have a block that has been considered as valid, but that will eventually be invalidated because the blob data is not there. And that can be used to force another subchain that the attacker has been maintaining. Okay, so that's a problem, and this uncertainty can last for a pretty long time, the time it takes for actually doing all the sampling. Okay, so the tight fork choice looks better, but it's obviously something you have to be careful about because the check has to happen within the first 4 seconds. Okay. If we look at the efforts that have been ongoing in the community for that, we have several efforts. Okay, some actually were funded by the Ethereum Foundation. There was an open call, and some actually proposed to use the existing Ethereum peer-to-peer mechanisms, those that are used to spread the blocks in the first place, to also spread blob data. Okay, the problem is that if you have many small subsets of the node that have to receive subsets of the data, like different lines and rows and different columns in the blob data, then you have very high latency. Okay, and the only thing you can do is to support this trailing fork choice. So in what follows, I will show in very brief what we proposed, which essentially is a system that enables this tight fork choice rule. The idea of doing the checks of availability of L2 data together with the check of the validity of the L1 block in the same 4-second period after issuance of the block. Okay, so that's what we call pandas. It's not the official logo, but it's a system that does not use the P2P mechanisms of Ethereum like Gossip Sub, but builds new ones that are fit to respect this 4-second requirement that we have for checking availability of data. Okay, and we essentially build upon 2 pillars. The first is that we leverage this proposer-builder separation that has been also introduced in Ethereum. I'm going to give a very quick glance at that next, and doing one hop or direct P2P communication between the nodes using some smart ideas that I will briefly mention next. Okay, so if you want to have a full description, because I'm not going to go into the details, we have a paper about that you can check on Archive, and it's currently being evaluated for a conference, but the paper is already available for free. Right, so how do we handle this dissemination of blob data? So we first build upon PBS, which is short for Proposer Builder Separation. So this is something that has been implemented in Ethereum for quite some time already. And it comes from the realization that the production of blocks, so putting together the blocks with all the transactions, becomes increasingly complex. Okay, and if you leave ordinary nodes to do that, and also because you have this maximal extractable value that is coming, then ordinary nodes will be essentially left aside and decentralization will suffer. Okay, so that's a something that the community realized quite quickly. And instead of saying, well, that's the way it goes, and then we only have these very powerful nodes and a few participants can build a system, Ethereum decided to split the roles of building blocks, which can require some beefy nodes and so on, and selecting it or participating in consensus. And those 2 roles are handled by different nodes. So you have powerful builders that prepare the blocks, and ordinary nodes, could be a laptop, it could be a node that you maintain at home, support validators, and those are the ones that have stake and that are elected to be proposers and propose new blocks, or be committee members and validate those blocks. So the PBS and data availability samplings are intimately linked. In fact, in Ethereum, those two are considered that they can't be separated, because if you have to prepare those 32 megabytes of blob data, you have to collect it from the L2s, then you have to do erasure coding, and so on. That requires ample computing. So ordinary nodes will not be able to do that as well. And what we also posit in our work is that the seeding or the sending of the data to the network, in order for it to be available and checked as so, must also be the responsibility of the builder. Okay, so that's something that we build upon. Just because I will probably not go into all the details, I can maybe show the other slides if there are questions, but this is how it works on a very high level perspective. We have the builder here that generates the block, as we did before, a blob that is attached, a proposer that is an ordinary node that is selected by this proof of stake, this election, selects the block from this builder or another. There is a market for blocks, essentially. And then when this block is selected, the builder is responsible for sending subsets of the data using a certain strategy. There are different possible strategies, but it sends subsets of this data to the system, to all the nodes that form the Ethereum infrastructure. And then those nodes, they will interact between each other to consolidate the data and get entire rows and entire columns so that they can serve to the L2s when the L2s will need them, and also check that the data is available by doing this sampling for a certain number of nodes of cells in the system. Okay, so that's what is written here. They do the builder sends the data to the system, and then the nodes interact using direct P2P communication to consolidate and sample. So importantly, they don't use gossip sub or other mechanisms that require the construction of dissemination structures. Everything happens by direct communication. Okay? So I'm going to spare the details. I'm just going to show that slide before jumping to my conclusion. This is the evaluation. We've built that using the existing Ethereum network stack, which is called libp2p. And we've implemented it and deployed it over 1,000 nodes in a very big cluster. And essentially what we get here is that we respect, and that the important curves here are the light blue ones here. We can see that we are within the 4 seconds for the vast majority of the nodes, even in a system where you have wide area network latencies, meaning that some validators might be in Brazil, others in Asia, and so on. And that is something that none of the existing mechanisms for dissemination and networking in Ethereum can yield. They are systematically above that 4 second threshold. We are also pretty robust to failures or to some subsets of the network being unavailable, but I'm going to skip that. And I'm going to conclude now because I'm over time. Right, so to sum up, in Ethereum, the primary mean for scaling out the throughput is to use this 2 hierarchical system where you have the layer 1 that stays as it is, and it acts mostly as a settlement layer only for very high value transactions, and it provides a data availability layer with this Danksharding idea and erasure coded data that is sent out to the system, and the layer 2's rollups primarily will be used for executing the bulk of transactions. Okay. And this comes with its own set of challenges, like networking challenges to send that to the network. And we briefly touched upon that. It's still something that is in discussion. I'm not claiming that our proposal would be the one that would be eventually chosen. It's just one that we put on the table. We hope to engage with the community further now that the paper is out, to see if that's or a variant of that is adapted. And that's all for me, and I'm happy to take questions. Thanks.
Okay, since we are on track, let's start directly with Sushmita presentation, okay?
Okay.
Thank you very much for the invitation. It's really a pleasure to speak here. And thanks, Etienne, for your wonderful presentation. I'm going to touch upon some of the concepts, what we need for post-quantum cryptography here. So before I start the talk, I would just say what before I talk about the plan for today, I would like to thank the traditional owners and custodians of the land from where I'm speaking, and pay my respect to elders past, present, and emerging. So what we'll do today is give a background on post-quantum cryptography and why we need post-quantum cryptography. And then we'll see why we need post-quantum cryptography for blockchains, and what do we think of blockchains, or what perspective of what are the things in blockchains we should concentrate if we were to migrate to post-quantum, and what could be such a migration plan. So I'll start a bit of a background because quantum computing is something that is emerging. It has so many interesting applications that there has been extensive research and development in quantum computing now. So just to give a background, though it has been for a while, the idea was proposed by Richard Feynman. From our perspective, the important breakthroughs are that of Peter Shor, who proposed a factoring algorithm, who proposed to break the factorization problem, solve the factorization problem quickly using quantum computers. However, what I would really like to mention is that there were two breakthroughs. One was Peter Shor's algorithm. The other one was Grover's algorithm, Grover's search algorithm, and these are the ones that that has impact on cryptography, and I'm going to say how. Just to have a look into what the current state of the art was and how it has evolved over the years. So the first 2-bit quantum computer was realized in 1998, and after that we have seen quite a bit of advancement in quantum computing. Over the last few years, there has been quite big leaps in this scenario. And some of us, if you're following this, this domain, we have seen two major breakthroughs last year with the Majorana chip from Microsoft and Google's Willow processor, which essentially says that it would be much easier to develop quantum computers with precision, making it important to look into the cryptographic side of things. And I'm going to say why it is important, to think about post-quantum cryptography, and what are we doing about it. So before that, just let me say, like, cryptography is everywhere, and you would see that whatever messaging app you use, or the messaging apps, our blockchains, any kind of digital ID verification, fetching your bank website data, and making transactions on the bank website, everything uses cryptography. So the major threat to quantum computers is because of two things, two algorithms. One of them is Peter Shor's algorithm, which can factor large numbers very quickly compared to classical algorithms. The other one that has also been a very recent advancement in this literature is that of a fast factoring algorithm by Oded Regev in a couple of years ago, which was an important improvement over Show's algorithm. The reason why these threaten public key cryptography is because we do have many of the public key algorithms depending upon problems which are hard in the sense that they rely on some number theoretic assumptions, including factorization problem, for example, in RSA, which would render these problems easy to be solved, and therefore the security of existing algorithms would be compromised. And that is the reason why we are really concerned about the current state of the art of public key cryptography. Now, there's another algorithm that I would like to mention is the Grover search algorithm, which can speed up structured search quadratically. What it means is that many of the symmetric key algorithms would demand larger key sizes. So essentially, the big difference between the impact of quantum computing to public key cryptography versus symmetric key cryptography is that in public key cryptography, your underlying assumptions, hardness assumptions, are broken. So you need to have algorithms which would rely on other assumptions, other hardness assumptions. So you need to change your algorithms altogether. However, with the symmetric key algorithms, the algorithms remain intact. However, the key sizes needs to be changed because that's what Grover search is essentially going to do. It is going to reduce the search space, and that's where you would demand larger key sizes, and it can be done without changing the algorithms themselves. So we are going to look into public key cryptography and the newer algorithms that are that can resist against quantum attacks. So one of the important question then is what would be, how much what sort of powerful computers, quantum computers, are we talking about? So it has been shown that around 10 to the power of 6 or 10 to the power of 8 qubits approximately are needed to break 2048-bit RSA. Now, the question comes like how far are we? And this is something that researchers are talking about nowadays, and everyone is talking about nowadays. It's called the Y2Q, which is essentially year to quantum, meaning that the anticipated time frame when quantum computers will be powerful enough to break widely used public key systems. And the reason I'm talking about this problem today is that this problem is very important. We need to address post-quantum, the threat that's coming, that is imminent from quantum computing. And as a result, we need to act upon this as soon as possible. And I'm going to say why we need to act upon it soon, because it's not a very easy process. And I'm going to show you with the example of blockchain, why is it very hard problem to migrate everything to post-quantum cryptography, and why we need to really start now so that we can be safe. Okay, so one thing I would like to mention then is that what is the impact of such a quantum threat? So if you think about it, many of the algorithms that will be impacted are RSA because it relies on factorization, hardness of factorization, and then we do have discrete logarithm being also impacted by the quantum quantum computers. So essentially, RSA, ECDSA, EDDSA, ECDH, Diffie-Hellman, all of these are impacted by quantum computers. And if you look around, you would see like many of the network protocols, digital signatures, when we are using TLS, SSL, VPNs, these are all impacted. Which also impacts many industries, including banking, finance, blockchains, cryptocurrencies, e-health, and so on. So because the threat is imminent, and we do have a large number of algorithms and protocols, as well as applications being impacted, we should really be start thinking now. So as an important consideration, now there are a lot of initiatives, and every country seems to have their own roadmaps to how to approach this issue. And for example, by 2020 from now to 2035, there is going to be a large number of changes, and we need to make sure that companies have migration strategies. So, for example, NIST has a migration a guideline for this migration and timelines for migration. Why this is important? Because according to these guidelines, many of these algorithms would be either deprecated or completely, would be simply not going to be used by 2035. So this is the time when we should be starting to think about post-quantum and migrating to post-quantum. So, for example, very recently, EU has proposed a roadmap. Australia, US did it a year ago. So there's a lot of discussion around this. So one thing to keep in mind is that we need to protect against quantum attacks. And what should be the strategy to protect against quantum attacks? So there are two well-known ways to address this problem. One of it is using a quantum key distribution. So instead of Diffie-Hellman, we use quantum key distribution. However, this is disadvantages are that these are very costly processes. They might not scale very well. However, with post-quantum cryptography, we are still working on the classical domain. And we use security assumptions that do not break under quantum attacks, like hardness of lattice problems, symmetric key-based schemes, and so on. There's another way of looking into things, which is hybrid schemes, which use a mix of QKD and PQC. And over here, different countries have different take on what technologies to adopt, technologies to use. So for example, in Europe, it's like the hybrid approach is a preferable one. In the US, it's the PQC. In US and Australia, PQC has been proposed as the way to move forward. So maybe I'll just take a quick, just check quickly what we have been doing at UNSW. So we look into a number of from across this landscape. We look into different type of problems at UNSW. So from the foundations perspective, so we are looking into post-quantum signature schemes. So in my team, we are mostly looking into hash-based and MPC in the head-based schemes. And also post-quantum commitment schemes. And I will tell you why these are really important when we think about blockchains. At the next level, from the protocol perspective, we are looking into network protocols, which essentially include DNSSEC, VPN, and various identity protocols. And one of the things to keep in mind is that there's a whole lot of work that needs to be done because though some of the post-quantum algorithms have been standardized by NIST, many of these cannot be used in a plug-and-play fashion when it comes to network protocols, and I'm going to say why that's not the case. Regarding applications, we are looking into blockchain application as well as privacy-preserving machine learning applications. Mostly for finance, health, and telecom, but this is not restricted to only these three domains. And the last one is that of post-quantum migration. So there are two things that we are doing at the moment. So migration from the technical perspective, which essentially would be how do we what are the steps to consider in migration and how do we proceed towards it? And I'll talk about it in a bit in the next couple of slides. And there's also some initiatives we do with our law faculty, which is towards really influence the regulatory space, the technical aspects and the regulation aspect, because it's very important that we not only design the technology, but also help in the adoption of that technology. So why is it important for blockchain? So if you think about blockchain, the way blockchain work is that, say, for example, Alice and Bob are making a transaction. You have to sign the transaction. A number of transactions are put together in a block. These blocks are broadcasted in a network, and then there's a consensus algorithm that is executed, and finally the block is added to the blockchain. This is at a very high level what happens in a blockchain. Now, if you think about each of these steps, there are many cryptographic ingredients that are used in blockchain. So what are the ingredients? So one of them is the signature. So you are signing a transaction. Then the next one is, for example, the hash functions. So hash functions are important because we want to ensure that transactions are immutable. And for example, Etienne just mentioned that, we have the Merkle tree, which has where we take all the transactions, club them together, and have some kind of an authenticated data structures to ensure that none of these transactions are modified or modified. And similarly, blocks are also the hash of the one block is fed into the next block, meaning that you cannot change the blocks and help guarantee the immutability property. So there are many other ingredients that go into it. Say, for example, commitment. You send a commitment committing to a transaction. You use some of the blockchains use verifiable random functions, which are used in the consensus mechanism. So, for example, Cardano, Algorand, they use verifiable random functions, which are again interesting cryptographic ingredients that we should be considering. So, and definitely there's a lot of work that is being done in zero knowledge proofs for blockchains, because as we saw just in the last talk, that the rollups, for example, they are using zero knowledge proofs or any a non-interactive proof or a snark proof. And again, that's a cryptographic construction that we need, a cryptographic ingredient that we would need. And again, privacy-preserving blockchains use zero knowledge proofs as well, for example, Zcash and many others. Okay, so wherever there's cryptography, not always it's like quantum threats, but in the case of blockchain, there are certain things we need to consider when we talk about when we think about mitigating these. So, for example, a very simple example is that of forging a signature. So currently, the signatures that are most widely used, for example, ECDSA signatures, these can be broken with strong quantum computers. So that's one of the things we need to keep in mind, because forging a signature means like I can say that, this is my secret key, and I will be able to say that, yeah, this is the money that I have sent. So the problem with the quantum threats is that signature schemes like ECDSA needs to be replaced. Similarly, you could manipulate the consensus algorithm if you could modify the verifiable random function that was being used. And then you could also compromise privacy or within certain blockchains which use, say, for example, zero knowledge proofs, because these can also be impacted. Some of the zero knowledge proof protocols could also be impacted with this. And just before, when Etienne was talking about the role of KGZ commitment, so that's again one of the things that is going to be impacted. This is just a timeline that shows this migration, I would say, not a migration plan, but couple of things I would like to mention, because when we think of post-quantum cryptography, we always tend to think it is a very recent phenomena. However, the underlying threat was not unknown to cryptographers. There has been a lot of work that has been done over the years in protecting, developing other ways or other cryptographic algorithms that do not rely on some of the number theoretic assumptions that we see now. And one of the earlier works is that of Lampert signature. So I remember when I was a student, maybe 20 years ago, and I learned about Lampert signature. It's a hash-based signature. It never struck me, or I never thought that one day this is going to be again studied in a way that and number of signature schemes would be built on these Lampert signatures. These are hash-based signatures. And similarly, the lattice-based constructions, for example, Entrio and many others, have been there for a very long time. Why I'm saying this, because there has been really tried and tested algorithms that have been there for a long time, and now we are seeing them in the mainstream post-quantum space. Two things I would like to mention, and this I talked about just now, is that the NIST competition, that NIST essentially standardized some of the constructions for post-quantum chems, key encapsulation mechanism, as well as signature schemes. So the competition started in 2016, and we have over the last few years we have seen multiple rounds of this competition, and finally we have NIST has selected a few candidates, which is going for FIPS. Which has been standardized and and a number of them are also being considered. So when we think of cryptography for blockchains, so what is it that we need to really think about? So if you think from the foundational perspective, what are the things like, for example, signatures. Signature schemes need to be replaced. Commitment schemes need to be replaced. Not always. So I'm going to talk about what needs to be replaced and what can stay as is. So this slide is about what are the things, what are the basic ingredients. So for example, signatures, these are basic ingredients. Commitments, it's a KGZ commitment. Then the commitment, like a Merkle tree, is also a commitment. verifiable random function that we talked about. And then there's multi-party computation, zero-knowledge proofs, multiple zero-knowledge proofs. Not all needs to be changed. Then we have the secure protocols that are used in many applications. And then we have applications. So for example, various privacy preserving applications that are run on blockchains, identity verification, and so on. Now, do we need to replace everything? No, not at all. So much of the cryptography is not quantum safe, but there are many things that really we don't have to worry about much. So as we talked about just a couple of minutes ago, ECDSA is something that we need to replace. Commitment, for example, KGG has to be replaced. Then within zero knowledge proof, Groth 16, Plonk, that have been widely used in the constructions of SNARKs are going to be have to be thought about being replaced. And then we do have TLS and so on. OAuth, for example, verifiable random functions, and so on. Now, with the NIST standardized algorithms, there are 5 main classes of NIST standardized algorithms from the symmetric key primitives, hash-based, MPC in the head-based, and vol-based constructions. And the standardized ones are in blue. So Sphinx Plus is something that has been standardized. XMSS, which has been a hash-based signature scheme for a very long time, has not been standardized, but we will see that there is a discussion about using XMSS for Ethereum blockchain. Similarly, Picnic was in one of the finalists for the NIST, which was not standardized. NIST also has another additional signature scheme competition where the Feast is one of the very attractive candidate for that might be that has proceeded to the recent rounds. Similarly, lattice-based constructions, we have Crystal, Kyber, and dilithium. Crystal, Kyber, dilithium, and Falcon that have been standardized. And with the code-based, we have Hamming, quasi-cyclic, or HQC that has been standardized. Macaulay, which has been there for a long time, which has not been standardized. And there were many considerations that were made while in the standardization process, and not just security, but also the performance in software, hardware. This included key sizes, verification cost, for example, signatures, and many other parameters, many other considerations. We have multivariate and isogenies, which are again something that have been in this, different types of PQC algorithms. And we do need a diverse portfolio. And this is very important to note, because the reason for this is that, many of these lattice-based constructions, for example, we don't know whether they are secure, but again, we don't know whether they are it can be broken or not. So, the provable guarantees are really important, but at the same time, still we are able to, it's like it has not been proved to be proved, or it has been disproved. So we are at that juncture where we do not know what's going to happen. And that's why we have a diverse portfolio, because if something, if we are able to break one of these underlying assumptions, then, we can proceed with the next one. And there has been also several PQC algorithm applications, and very important for us are generally, definitely network protocols, but also zero knowledge proofs, which are extensively used nowadays in the blockchain community. And if you look around, you would see that, the Stark community is doing fine, because these are quantum resistant. And, there are a number of projects projects that are built on snarks are essentially, going forward. The reason why it is, as I said, like you cannot plug and play with this post-quantum algorithms. The reason being that sometimes large key sizes, or maybe large signature sizes, or even sometimes the different restrictions on the different formats, which make it very hard to use in a plug and play fashion. So if you say like, okay, fine, ECDSA is insecure, just let me replace it with dilithium or Falcon. No, it's not straightforward as we think, because we have to think about what is my signature size, how quickly can I verify, how quickly can I construct the signature, and so on. So there's a lot of considerations to be made when we are transitioning to post-quantum cryptography. So I'm not going to talk about this. This essentially says that organizations should have a migration plan, that the amount of time the data must remain secure, plus the amount of time to upgrade the cryptographic system should be greater than the time when the quantum computers come and online and have enough power to break cryptography. So one thing I didn't mention is that there's a bigger threat, not just signatures as we see in the blockchains, but there's a bigger threat which is called the harvest now, decrypt later. And this is a very big concern for financial organizations. The reason being that we can harvest or collect a lot of encrypted traffic now, and maybe when the quantum computers come, the adversaries can decrypt it. So there's a very important, very scary threat, I would say, which is a harvest now, decrypt later threat. And that's what is often considered to be a very big threat to this community. Now, with saying all that there is a threat, what are we supposed to do? And what are we supposed to do for blockchains? So if you think about any organization, they have migration strategies, and these are the 3 steps of the migration strategy. So first of all, you built an inventory of all the cryptographic assets that you have within the organization. And it could be your, various cryptographic hardware and software. You can have like a lot of files which are encrypted. You can have a number of protocols that are using cryptographic algorithms and protocols. So there's a whole lot of things that you need to make sure you have the complete list of cryptographic assets. Once you have a cryptographic list of cryptographic assets, the organization would try to figure out what are the dependency between these assets and make a decision what needs to be migrated and in what time frame, because it's not very easy to migrate. It requires investment in terms of human resource. It needs investment in terms of time and building all that knowledge, so it's a lot of a big challenge to figure out what needs to be migrated. And once the organization has makes a decision, then it would have like select which algorithm to use, alternatives to use, and carry out testing and performance and documentation. If you look into the migration for blockchains, it's a little bit different, I would say, because organizations are mostly, the decisions are taken by some centralized entity. So, for example, the board might take a decision on what to do. Or, the CISO is the one who would have a team and, think like, okay, how do I migrate? What is my budget? And so on. With blockchains, it's not very straightforward because most of these are decentralized. Often you would have like a hard forks if you were to move to something else. And one example is the case where we saw proof of Ethereum's move from proof of work to proof of stake, which was essentially a very long process and had to be extremely smooth. So Some of the important considerations for blockchain is to first design primitives and protocols that are quantum safe. For example, exotic signatures. For example, you need aggregate, blind signatures, ring signatures, and so on. Pablo, I know I'm like, on the verge of time, so I'm like quickly, you have a couple of I think three slides over here. So, for example, blind signatures, ring signatures are also something to consider. How would we migrate? For example, Monero uses a ring signature. So what happens if I replace the ring signature with a post-quantum variant? How do we consider migrating to that? And then post-quantum ZK snarks are some things we need to think about. So at the fundamental level, designing primitives and protocols that are quantum safe, identifying cryptographic protocols that are unsafe. So for example, we have been talking about ECDSA, BLS, KZG, and so on. What are the alternative solutions that measure performance and feasibility? And I'll talk a little bit about, some of the initiatives that are being taken by Ethereum or Cardano community and many others to see like what would be their roadmap for this post-quantum transition. And this is really important because if you want to integrate a post-quantum variant, we need to understand how the performance will be impacted. What will be the feasibility of that algorithm in the scheme of things? And then there's a diverse solutions to be considered. So whether it would be hash-based or lattice-based or isogeny-based and so on. So, and then the migration execution is another big challenge. There's already some work that is being done in this space. And I'm just quoting just three here, but there's a whole lot of literature that is being that has come up in the last couple of years on post-quantum blockchains, and I find these very interesting. The first two are definitely towards efficient for the Ethereum community specifically. So, for example, this is a recent paper that is going to be presented in Asia CCS this month. I think, next week actually. So I'm really looking forward to hear from the speakers about this talk as well. So this is about signature verification, post-quantum signature verification on Ethereum. Similarly, Ethereum community has already proposed hash-based multi-signatures on Ethereum. So these are using XMSS protocols. And from our side, we have been looking into some of the post-quantum signatures, aggregate and ring signatures using symmetric key primitives. So I do not want to go into deeper into any of these works, but just letting you know that there's already a lot of work that is coming up in the community to first build some of the basic tools so that those can be adopted in blockchains. So in conclusion, there's a lot actually to do in this space. So for everyone here, I would really say that this is a very flourishing area that has a potential for a lot of research and development activities, and definitely commercialization activities as well. And there's a lot of lessons to be learned from the merge. For example, post-quantum roadmap for blockchains is something I think is really important for all blockchains. And there has been a lot of active research and development in the post-quantum cryptographic world. So now it's a time that we, build this awareness and start training ourselves to be more equipped to help in this migration process, because migration is going to take time. And if we don't start now, it's going to be too late. And we will not make right decisions and do things hastily and create problems. Okay, so that's all for today. Thank you.
Thanks a lot, Sushmita, for the presentation. I didn't want to cut you, but yeah, the smallest question here could take longer than expected in these topics. So I also wanted to leave some time to the question and answer.
Sure.
Thanks.
So Vasilios asks, what are the ongoing roadmap efforts for transitioning existing blockchain networks, such as by the Ethereum Foundation and Bitcoin in the form of Bitcoin improvement proposals, so BIPs, or to support PQC, and what are the specific challenges they are addressing or need to address? So the Ethereum Foundation has been really active in talking about blockchain, and they have been putting up the blockchain the roadmap. So essentially, one of the things that I see from the community is that at the moment, whatever new proposals are coming up, these are things that they are considering, like whether this is going to be quantum safe or not. So there has been an effort towards really accepting proposals, or more interest in proposals which are quantum safe, that can be incorporated in the in Ethereum. And Ethereum community by themselves are looking into Ethereum foundations. Researchers in the Ethereum foundations have been looking into signatures, for example. And the paper that I said, the second paper that I mentioned, a couple of slides ago, is that by the Ethereum Foundation. So they are looking into multi-signatures, for example. And one of the things that I have seen happening in this community is looking into aggregate signatures, because as Etienne just said, that even when we are doing this attestation, there's a BLS signature often used for aggregating signatures, and they would like to replace BLS or other schemes with quantum safe solutions. I also feel that KZG is something that they are also thinking of replacing somehow, and their candidates, they have been looking into either lattices and some hash-based constructions, but I'm not too sure whether they are looking into just these two classes, or they are more open to the others. I have also seen Cardano's roadmap. So they are also they do have plans of moving things to post-quantum.
I would actually have one question, if I may. It's more a curiosity question. So in Bitcoin, in the very early days, you had public keys were recorded on chain, and that was later changed to have this pay to public key hash instead. So instead of putting in the chain, in the locking script, you have now only an address, which is essentially a hash of the public key, and the public key is revealed only when you actually spend and spend output, right? So when you unlock, where you have a transaction that unlocks, okay, so that's really specific to the UTXO model, but is this idea of just sharing an hash of the public key enough for PKC, or is it also something that could be broken with quantum computers? So
yeah, so I think the signature scheme itself has to be replaced.
Okay, so if I share, so there could be ways to derive a valid public key from hash also.
So it is possible to forge a signature. So even if you have not done the signature, I can forge a signature and claim to be, a valid signature on your message. So that is possible to do. And I think that's something of a challenge for us. Okay.
So if I have a quantum computer, I can become very rich, I understand.
Yeah, that's true. That's true. That's true.
Etienne, I have a question for you.
Sure, go ahead.
Because you were speaking about the 4-second window, and what really are the risks if block propagation exists these times? Because thinking about post-quantum in the future, we are seeing that the cryptography will take longer times to process the data, and this window might be too small for this future, right? So
that's okay. So if I understand well, the question is the now we have more complex schemes, and the verification of a block might take longer because the complexity of the operations, right?
yeah, exactly.
So
I
yeah,
don't really know the risks for exceeding this 4-second window, but
in
in the future,
in the current
probably we will.
Ethereum, if you are a validator and you are in a committee and you fail to give an attestation by these 4 seconds, you essentially consider you lose your reward, right? So you are at least at risk. The risk that you have is that you lose your reward. Okay, so if a few validators miss the deadline, or if the validators are offline, a few of them, it's fine because it's essentially a majority vote, a super majority vote. If more than a majority actually fails, then you're in trouble because then you simply will have missed slots, and there will be slots for which you don't decide on a block, and you will reduce the number of blocks per hour or per epoch. Now the thing is that if really it becomes extremely costly to verify the transactions, the thing is that in Ethereum it's not like in Bitcoin. In Bitcoin you have transactions have operations that are themselves crypto operations, while in Ethereum you have this Ethereum virtual machine. So it means that if you have something that takes more complex operations, it will take more gas, and it will essentially reduce the amount of transactions you can put, because the gas is the limit, and the gas more or less directly translates to the amount of time it takes to run the transactions. So if you have something that really does a lot of computation, then it probably will simply limit the number of other transactions that can go into the block. And that's how you limit how much computation is necessary to rerun the transactions. Now, of course, if you have, and that's the problem with zero knowledge proof mechanisms for rollups, but also for other usages, that you can have things that really are extremely costly, and the first it costs you a lot because you have a lot of gas, and then it limits how many transactions can go into each block because of that gas limit. It has been increased, but it cannot increase beyond a reasonable threshold. So yeah, I hope that answers.
Thanks for your answer. We have one hand raised from Giuseppe.
Referring to the question that Etienne made on Bitcoin, you meant that someone can simulate a signature which is approved by the system, or can be reversed, the hashing mechanism. It's not reversible theoretically, the hashing mechanism. It's just that someone can fake.
Yeah, forge.
Okay, so they can fake a signature.
Mm.
Or create something that can be approved.
Yeah, exactly. So I can create a signature, and maybe you can think like, this is a valid signature, and I can, that's what could go wrong.
I was just having the concern about the reversibility of hashing functions. This is not breakable.
Reversing a hash function, I think hashes, hash functions themselves, the one-wayness of the hash functions, these are not impacted by PQC. Yeah.
No, I understand, but the risk is there anyway. Okay. But at least the math is safe. Okay.
Yeah.
For this UTXO, for the Bitcoin, I think that because you have this UTXO model, you can use the transactions output only once.
Yeah.
So you disclose the associated public key only when you actually use it. you should be fine. Well, maybe because if you can't reverse the hash function, then you can't, and when you disclose the public key, it's too late because now the output has been used and the nodes will not, you will not allow double spending even if you can, if you can break the public key cryptography scheme. So maybe UTXO is more robust on that respect, even though it's more complex to support smart contracts.
Thank you for the clarification.
I think we can really close the session and thank both of the speakers and also the participants.
Thanks.
Thank you,
Anna,
everyone.
Thanks for the invitation. Nice.
Thank you. Thank you for the
Thanks
invitation,
for-
and thanks everyone for joining. And thanks, Etienne. Your talk was very nice. Looking forward to read your paper.
Yeah. Thanks a lot. Thanks.